I wasn't sure what to talk about, so I decided to give 5 talks. Each will be about 5 minutes. So fasten your seatbelts. But these are all topics that have to do in the spirit of ask not what machine learning can do for control, but ask what control can do for machine learning. So it's a very Kennedy-esque version of things. Anyway, so the first topic, very quickly, is about autoencoders. So let me remind you, the manifold hypothesis, it's not a theorem or anything like that, but it's the idea that maybe data usually are in a very high dimensional space, but they lie on a submanifold of, say, dimension little k. Okay, so one would think that one would want to have ways of detecting the dimension of this manifold, and we know, of course, if everything is linear, we use principal component analysis or whatnot. But if things are nonlinear, a typical approach is to use autoencoders. So what is an autoencoder? An autoencoder is some sort of neural network type system in which there's a middle dimension, which is relatively small. In this case, we'll ask the question, suppose we have a manifold of dimension k, could be a manifold, it's a compact manifold with boundary or without boundary, and we're going to assume that the problem of interest would be, can we find a neural network in which we have an encoder layer, a middle dimension, which is equal to the dimension of that manifold, and decoded so that the composition gives us the identity map on the data manifold. Now, clearly, there's an obvious topological obstruction. I mean, if you have, say, a circle, you're not going to factor it precisely through a line, right? There's obvious topological obstruction. So, the reasonable thing is to ask, well, what about if there's, can we get some approximate things? So the first thing you do is you throw a deep neural network this, or a coder neural network this, PyTorch, whatever, train. And you see that what the network will tend to do, and this example is, I did quickly an example with 2 circles, 2 interlaced circles, and you actually get a pretty good reconstruction. Of course, what's going to happen is the circles are going to be broken up at one point, okay? And the 2 circles are going to be mapped into essentially 2 disjoint segments, okay? And then you go back, and what's going to happen is the reconstruction actually looks pretty good, but there's little gaps in the reconstruction, dealing with the fact that you couldn't, of course, approximate things exactly. You couldn't get the identity map factored through this trivial topology case. So that leads to asking, well, what kind of theorems are there? And to my surprise, apparently they weren't. I mean, maybe you'll tell me there was some theorem out there that tells you why autoencoders should work. But we wrote this little paper in Transactions of Machine Learning Research, just appeared this year, with Matthew, in which we proved, and there's a lot of words in here, and it's late, and I don't want you to have to read through all the details, but basically what this says is that it's sort of like a pack type of way of thinking of things. For every epsilon and every delta, there's a set of measure less than delta, so that you can actually build a network that is going to reconstruct with error less than epsilon, except on that set of arbitrarily small measure, okay? And that's basically what this is saying. So that's sort of a positive result. A negative result would be, you could ask, well, can I approximate, if I give up on a perfect reconstruction of the identity mapping, how well can I do if I'm only going to look for an approximate reconstruction? And then one theorem is as follows. Suppose we define the reach of a manifold. This is a concept that was used, for example, in papers by Charlie Pfefferman and others. We define the reach of the manifold. It's sort of a measure of local curvature, if you like to think of it that way. You look at the smallest, the largest number R, so that if you are outside the set, typically a non-convex set, that if you're outside this set, think of that as our manifold with boundary or whatever. If you have the inside will be a manifold with boundary, the outside will be a manifold without boundary, it doesn't make any difference. The smallest, the largest distance, so that it could project uniquely into a point in there. So for example, here, if you go to this distance, there's 2 projections, 2 perpendicular projections, right? 2 minimum distance projections, so the reach cannot be larger than that. Theorem, that gives you a lower bound on the possible approximation that you can get, okay? So how do we, and by the way, if you actually look at this, you get exactly, when you look at what happened in that example, that numerical example, you get that reconstruction area is very small, except in a very small area, right? And except in the small regions, corresponding to breaking things at a small set. In terms of how you prove these things, one last thing in terms of comparing the two results. So yes, I gave you an epsilon delta version, but you could also change this into an L2 version, which makes more sense if you think of empirical risk minimization. So you could also rewrite the result by saying, the first theorem, by saying that you can get arbitrary small L2 error, or LP error in any P. In fact, any measure that is, non-singular with respect to Lebesgue measure or something. So, so in terms of proofs, in terms of the topic of dynamical systems, I'll be talking a lot about gradient systems today. So one of the ways that we can try to prove this is as follows. We start with this manifold that we want to approximate, and the first thing we do is we find ourselves a Morse function on that manifold, a polar Morse function that has a unique global minimum, local and global minimum, and you just look at the height function basically with respect to that Morse function. Okay, so you look at it, and you look at it, or let me put it with a height function in the case of the torus, let's say, and the proof simply goes by saying if you have a Morse function, then the union of the stable manifolds of all the equilibria of the gradient systems, all the critical points, has measure 0. And the complement is actually a connected set. And in that connected set, you actually have a global asymptotic stability in that open set. Therefore, that's diffeomorphic to Rn. So that gives you your actual diffeomorphism. And then you have to fatten the set and make it work in various technical ways. But that's the basic idea. So it's a gradient system to be able to establish a positive result. In terms of the negative result, that takes a little more work. Well, about the same amount of work. But basically, if you are within the reach, you can actually build a projection into the set that factors through Rk, and with a little bit of singular homology, you can actually get a contradiction. And you have to do homology over Z with coefficient Z2, but I can explain that if you're interested later why. But there's a little bit of algebraic topology to show that you cannot do better than the reach of the manifold. This is work in progress, where we're actually looking at extensions of this to vector fields. So suppose you have a vector field in your k-dimensional manifold. We would like to factor this through a vector field on the narrow layer, okay? And that's of interest in principle because of things such as trying to do image processing, right? So you've seen these things, I'm sure, a lot in the context of movies and compressing movies and so forth. So that's one of the little stories. I'm going to skip those other things. Second story, I wanted to connect a little bit to Igor's lectures tomorrow. So we heard a lot in the previous talk and a bunch of talks. We'll hear much more tomorrow about Koopman operators, the idea of Koopman operators, Koopman analysis. I should say Kalman because Kalman told me this, back in 1972 when I became his student. He told me this is what I should work on, and my PhD thesis was about exactly this sort of Koopman operators. We didn't call them Koopman, obviously. But anyway, the idea would be that you have some sort of nonlinear system. You'd like to embed that in a linear system, and for example, using adjoint operators in the Koopman case. The goal, of course, as we all know, is to somehow if we have an infinite dimensional linear system, which we always have in some abstract sense, back to Koopman and the original work, but we'd like to find some sort of finite dimensional invariant subspace that is enough to distinguish the dynamics. And once we have a finite dimensional space, of course, we can use linear control theory to do anything we want. So the little question that we asked ourselves was, can we prove any theorems that say when you cannot do this, when it's impossible to find a finite dimensional Koopman representation, perfect Koopman representation? So let's think a little bit about this problem. So the first thing I would think of is, well, if you have isolated equilibria, a discrete set of isolated equilibria, then of course, you shouldn't be able to embed that in a linear system. But that's not quite true, right? Because in principle, you could have a linear system with a non-trivial kernel for A. So for example, this could be the kernel of A, and maybe you could embed your nonlinear system that was that system in there with two stable and one unstable point. You maybe could embed it in this sort of, in this way in a two-dimensional plane so that you intersect the kernel of A at exactly 3 points. And then, in principle, it should be fine. However, it turns out you cannot do this. And this led us to understanding what's really going on. So the setup is the following. I'm going to assume I have a dynamical system on evolving in some sort of a forward invariant subset of a path connected manifold, say second countable manifold. And I'm not going to worry about a smoothness. They have to be continuously differentiable if you want. I don't care, Lipschitz. The key property that we study in this paper is the paper that I'll give you a citation in a second. The key property is the property that we call the closed basins of attraction property. So the idea is assume that you have any omega limit set of this system, look at the set of all points that have this little omega, this capital omega, as its omega limit set, okay? Now, one can prove that for linear systems, such sets are always closed. In fact, one can prove that for any incrementally stable system, these sets are always closed, okay? That's a little technical fact, which is key to understanding what's happening. So for linear systems, you could have domain of attraction could be just omega limit set. The only omega limit set might be a point, or it might be a point even in the unstable case, or it might be, a point, a whole line in the case of, say, a saddle and so forth, right? And obviously those are, domains of attractions of those are always open. So the key result in this paper that was presented at the IFAC conference last year, and it's to appear in Automatica, is the following. In an extended version, it's to appear in Automatica. Let me say that a mapping psi from X, my original state space, into a new state space Z, think of Z as where the linear system will evolve, okay, is an immersion if the obvious diagram commutes. In other words, if you first map and then find a solution, is the same as if you first find a solution and then map. There's nothing, it's just the obvious thing there, okay? And of course, you have a Koopman type representation, you're going to have that in particular. So the theorem is as follows. Suppose that the trajectories of the system are all pre-compact, so they're all bounded trajectories. So you have to be a little bit careful because the domain of attraction, the domain X in which you're evolving might be an open subset in Rn or something like that. So I really want to say the closures of every trajectory are compact subsets of your domain where the system is evolving, okay? So assume trajectories are pre-compact and assume that there's a discrete number of omega limit sets, all right? So, but more than one. So assume that you have 2, 3, even a countable number of omega limit sets, okay? Then you cannot immerse into a system with closed basins, period. That's a theorem. No epsilons, deltas, nothing else. That is the theorem, okay? Very easy to understand. In particular, you cannot immerse into linear systems. You cannot immerse into systems that are incrementally stable. So I'm not going to show the proof of that, but let me just say that the theorem is very tight in the following sense. If you have an uncountable number of omega limit sets, then of course you could embed it in a linear system. I mean, x dot equals ax, x dot equals 0 has an infinite number of omega limit sets. Every point is an equilibrium, right? It's an omega limit set. So clearly, discreteness of the set of omega limit sets is what kills you, okay? It's always possible to do local immersions in various ways. Of course, you can do some sort of approximate immersions or approximate Koopman, and I'm sure Igor will talk a lot about those things tomorrow. If you drop the assumption of pre-compact trajectories, and there are counterexamples, Matthew, the same Matthew that was my co-author in the previous paper, he has a separate paper, was done in parallel, where they give a counterexample with his co-author to when you lie down on the trajectories, you can actually have immersions in linear systems. And of course, you can have immersions into discontinuous immersions, or you can have immersions into hybrid systems of various types. And our paper has a zillion examples of those things, but in the interest of time, I am not going to actually give you those. Let me just say there's some implications to learning from data. This is a little technical to read, so let me just go over the blue part. The blue part says that if I start collecting data at random from a nonlinear system, and if that nonlinear system has more than one omega limit set, but a discrete number of omega limit sets, then at some point I'm going to get something that is inconsistent with immersion into a linear system. So for a finite amount of data, in the asymptotic case, it's just a density result. It's not anything particularly deep, but you have to write it down carefully, but it's just what you would expect. So anyway, so that's that. And yeah, there's a number of I put the asterisks are for a longer lecture, so I'm going to skip those, but basically they're, but let me just actually, since I do have a second, let me just point out that one thing that is a little surprising is, in fact, you can get a isolated limit cycle. You can have a system with an isolated limit cycle that can be embedded into a linear system, and that's a little bit surprising, and that's actually an explicit embedding. Right? First, I thought that was impossible. It turns out you can do it. It's sort of a funny thing. You take a system that has a standard Hopf-bifurcation canonical form, take the origin away, so you have a punctured R2, and then you sort of fold things in some way into a cylinder, and you put that in a three-dimensional linear system. So anyway, it's funny that that can happen, but that's only one limit cycle, one omega limit set, right? So it doesn't contradict the fact. It's that if you had more than one but a finite number, then you could not embed. So that was sort of interesting. Yeah, I'm gonna skip this thing. So a number of people had, including Igor and so forth, had mentioned that apparently there's a limitation, but as far as I know, this is the first rigorous result proving this. Okay, let me talk about a different topic, but going back to gradient flows. So in optimization theory, typically we might have a system that we want to optimize in some way. Let's specifically talk about a minimization of a loss function L. So suppose we have a function L that we want to minimize, and we look at the gradient descent flow. The gradient flow or the gradient descent, Euler discretizes that, you get, of course, the standard discrete gradient descent. So let's look, but let me concentrate on the continuous gradient flow. So everybody okay with this? This is just a standard gradient flow or negative gradient flow. Eta is a learning rate, quote unquote, which I'll take to be equal to 1 in the next few slides. So let me remind you a little bit about the basic theory of some of these things. Let me call T the target set. So this is the set of x's where L of x is equal to 0. I'm going to assume for simplicity that the minimum of L is at 0, okay? It has a minimum value 0, I'm sorry. It could be at many points, but the minimum value of L is 0. So L is bounded below, translated to make the minimum value be 0. So the target set is the set of points at which L is equal to 0. In some empirical loss minimization or something, you would want to make that equal to 0 or as small as possible, right? Let me call C the set of critical points. So this is a set of points at which the gradient vanishes, which of course includes the target set. Let me look again. Let me make eta equal to 1 for simplicity. Let me look at the gradient flow. So what do we know about that in general? First of all, from Lassalle's theorem, we know that trajectories always converge to the set of critical points. That's trivial, okay? That's just standard dynamical systems. Maybe a little bit less well known is that in the standard case where L is an analytic function, so it won't work for ReLUs a priori, but it will work with hyperbolic tangents or any of these other things that you might want, like in neural networks. In the case where you have an analytic loss function, all omega limit sets are actually equilibria. So not only are there subsets of critical points, but in fact, the trajectories actually approach equilibria. They don't approach limit cycles or anything like that, okay? For analytic systems. That's actually a beautiful result. Not true for C infinity systems in general. So you need analytics, a beautiful theorem of Lukasiewicz. Lukasiewicz will appear twice in this lecture, as you'll see. There will be a completely different area in which Lukasiewicz appears, as I'll mention in a few minutes. So in particular, of course, if the target set is equal to the critical set, so if you have only one, you have no saddles or something, then you know that you're going to approach the target set, and points in the target set, to be precise. More generally, and this is actually takes a fair amount of work to prove carefully, but pre-compact trajectories converge to the set of all critical points except those that are strict saddles. So By a strict saddle, I mean you got a gradient system. You look at the linearization of the gradient system. The linearization of the gradient gives you the Hessian. So we know that the eigenvalues are all real, okay? Eigenvalues could be positive or negative. If there is a positive eigenvalue for the negative gradient system, that's what we call a strict saddle. In other words, there is a direction where you're really repelling, okay? We like a negative eigenvalue, I think, for the original Hessian of L or something goes to the negative sign. I always get the signs confused, okay? Anyway, so, and that's actually a very beautiful little fact, which is not so well known apparently, which I'm surprised, but it is there in the literature. Okay, so actually there's a theorem which I'm not going to go over. I put this asterisk, but let me mention it to you. Suppose you have a real analytic loss function. Suppose that you know that the critical set is a union of the target set and strict saddles. In other words, assume that you know, and you'll see where this appears in training of neural networks in a few minutes. So assume that you know that the points that are critical points, but are not the points where L is equal to 0, assume that you know that those points are actually strict saddles. Then, in fact, you know that, and assume that you know also that every trajectory of the gradient flow is pre-compact, and that usually can prove through conservation laws separately. Then, in fact, you can guarantee that except for a set of measure 0 of initial conditions, or if you like, a bare category statement, you can do that too. It's a union of manifolds, basically, countable union of manifolds in the end. You actually know all trajectories conversion points to points in the target set. I should point out that there's a subtlety because you could have a continuum of critical points, and the theorem is still true. And if you want, I can sketch the proof later for somebody. It's actually quite nice. All right, so now, very quickly, what's known about convergence of gradient flows in a somewhat different context that will be very important for what I want to talk next. So I said the Lukasiewicz would appear twice. So let me talk about the standard gradient dominance condition. So the gradient dominance condition in the global Pauli-Lukasiewicz inequality, PLI, I'll say that for simplicity, is a condition that the gradient square should be bigger or equal than some constant times the value of the function. So this says that if you're far away from your target, the gradient should be large, okay? That's a standard Pauli-Lukasiewicz condition. Under that condition, it's trivial to show that the derivative of L along time, this is L of x of t along the solutions of the gradient system, will be less or equal than negative lambda L, therefore you get exponential stability, okay? So that's standard, super well known. What is probably less known is that you can replace these conditions by, and thanks Kirsten for bringing this up before with the function of class K and class K. So there are three other types of estimates that I want to point to you. One is the estimate in which we ask that the gradient, I put the square is not needed, it's just for elegance with respect to the PLI condition. Suppose that the gradient is bigger or equal than some function of class K infinity of L. Of course, if it's linear, that still will be true, right? So a function of class K infinity is a function that is increasing and goes to infinity, okay? Continuous increasing, 0 at 0 and goes to infinity. A second kind of condition is when you simply ask that the function be bigger or equal than a function of class K, that the gradient be bigger or equal than a function of class K of L. And a final condition is simply asking that the gradient be bigger or equal than a positive definite function of K. Okay, a positive definite function is just a continuous function which is always non-zero. Okay, but it doesn't have to be increasing or anything. All right, so let me skip that. So why am I bringing all these conditions? Because from the point of view of stability, it doesn't seem necessarily interesting, but here is where I think things get a little more interesting. So one thing that has been attracting my attention for a few years now, a couple of years to be precise, has been the following question. Suppose that you have a gradient system, you're trying to optimize the system, but your algorithm that you're using doesn't have access to the exact form of the loss function. It can only consult an oracle. Now this oracle will return an evaluation of L, or an evaluation maybe of the gradient of L, okay? But there may be errors. The errors could be due to the fact that maybe when the oracle is giving us the estimate, there's an adversary that is changing things. Or maybe the oracle itself, or digital twin, or whatever you want to call it, is not really very precise. Or maybe, and this is actually, it's been done right now, in fact, there's an application in aeronautical engineering, somebody did after I published my paper. Suppose that you have a model that is simulating the physical system, solving an optimal control problem, maybe using receding horizon control, MPC, but you don't carry it to completion. You just stop the optimality calculation, you abort it because you don't have enough computing time or whatever, and you send back that result. It's not going to be quite the result that you wanted. Okay, so you get, or for example, in computer science nowadays, this word reproducibility is used a lot. Suppose that Boumediene and I are running an algorithm, the same algorithm, but each of us is flipping some coins while doing this, some stochastic gradient descent. Maybe we're presenting data in slightly different order or whatever. Are we going to get basically the same result or not? How reproducible is what we're doing? Okay, so how do we model that? Well, the simplest model, I mean, you can do it more complicated, but the simplest model would be we have a gradient system and we add some disturbance. This disturbance, let's think of it as some sort of input or disturbance that you're applying to the system. So the question we could ask is, okay, if we have this kind of disturbance and we solve this disturbed gradient system, how far are we from the solution of the actual gradient system? And in two senses, what are during the transients, how far are we? Can the errors get hugely bad during this computation compared to what the gradient system we're doing, which is actually decreasing L monotonically, right? Or we could simply ask about the asymptotics of this. At the end of the day, as t goes to infinity, are we getting a result that is close enough to L equals 0, for example, if that's what we're converging to? So what is a way to think of this? Of course, given it's me, for me it's natural to write this as an input to state stability condition, and you already saw the definitions in the previous, in Kirsten's talk, so I don't need to repeat them, but basically, and it's very complicated to think about this if you never thought about it before, but basically what input to state stability says is, you want that if there's some disturbances, you want that as you do your computation, you're not too far, you're not overshooting too much from what you would do if there are no disturbances, okay? And asymptotically, the effect of the initial conditions goes away, like a fading memory condition, and you're only asymptotically bounded by something that depends on the magnitude of your disturbance or errors or whatever you want to call them, this perturbation on your gradient flow in this case. So the key theorem is this one, the key abstract theorem, okay, is that if you have a K-infinity type of generalized Lukasiewicz condition, then you get input state stability. If you have this alpha of class K and not class K infinity, then you get something called, that you might call small input or bounded input to state stability. I don't have time to discuss it in detail, but it's just an input to state stability condition in which you have an a priori bound on how big your disturbances could be in worst case, okay? But once you give that, you get this ISS type property. And if you only have positive definiteness, then you get what is called integral input to state stability for the experts here who know what that means. I'm going to skip how ISS appears. I'm going to skip the dissipation inequalities, was what Kirsten was talking about, the ISS Lyapunov functions. There's a paper in Systems and Control Letters, which is Miroslav's journal right now, that discusses all this. A number of people, including people in this audience, Miroslav in the context of extreme seeking and so forth, have looked at related questions. But now let me talk about an application of this to a control problem. So the control problem I'm interested in is the following. Suppose that we look at the LQR problem that was mentioned several times here. Why looking at the LQR problem? Because it's the simplest problem that we can understand using these techniques, okay? So of course you want to use this for more complicated nonlinear problems as well. But let's start with the LQR problem. So suppose we have the LQR problem for a linear system. So we want to minimize some infinite horizon quadratic cost, where we have a cost on the states and a cost on the inputs. And we know, as Kirsten's slides, we know that there's a solution that can be written in closed form using the algebraic Riccati equation. Okay, this is for control, not for observation, but it's the same thing. And the interesting thing, and this goes back to work of Bill Levine and Michael Athens in 1970 or so, which was completely forgotten by many, many people, which had to do with direct optimization of K. So suppose that we just want to do, say, a gradient flow solution for K, all right, without actually knowing A and B and so forth, but an oracle tells us what is the value of that gradient? So you can write the equations and you can ask, what do we know about convergence of that? And a number of people have worked on this and done beautiful work in this area. Marian Faisal for the discrete time case, and Jovanovic and so forth have done a lot of work on this. So the main result that we have is that, as a matter of fact, the gradient system is small input ISS with respect to gradient noise. And in order to prove this, we had to actually work very, very hard, because the estimates that you find in the literature did not give you a Polya-Lukasiewicz inequality, contrary to when one reads and thinks that those papers are saying. It turns out that when you actually read what the papers are proving, they only give estimates that are valid on compact sets, and that constant actually goes to 0 as the set gets bigger. To actually be able to prove the result, you need to prove a global result. So this is a fairly complicated, long paper that should be appearing now in systems and control letters. And we go on to explain how the same results apply to the Newton flow, apply to natural gradient over appropriate Riemann metrics, and so forth. So that's the so the problem is challenging because you have a non-convex optimization problem when you optimize over the right. You're optimize. Sorry, let me just. I know I went very fast, but you reformulate the problem to optimizing over the feedback matrix of the feedback gain, okay? The K, like Miroslav had in his lecture, right? So you're looking for this feedback matrix, and you just work with that and the gradient flow for that guy, okay? Which implicitly goes to solving the algebraic Riccati equation and so forth, but assume that you're only given the form of that gradient, evaluated at a given K. You could think of a model that is a plant that is simulating things in a reinforcement learning setup or something, okay? So it's a way of understanding things like reinforcement learning, at least in an abstract way, applied to a very simple model. So the gradient flow is, it's a perturbed flow evolving in a matrix space. It's actually a complicated flow, but the main, I think I'm just going to go to the, the picture that actually shows where things are. So basically, we're able to show that the LQR problem is in the class of problems for which this CJS is a comparison just saturated condition, we call it, is when you have a class K function, okay, in the generalization of the Lukasiewicz inequality, the Lukasiewicz inequality gradient dominance condition. So, but there are different things that you could have if you could actually were able. Oops, sorry, I went back by mistake. If you actually had the PL condition, of course, you get exponential ISS, but you don't have that for the LQR problem. You can actually prove for the LQR problem you don't have that, contrary to what it would seem from the literature. So basically, this is what we proved in that paper. So let me talk about something a little bit different quickly, and this has to do with feed-forward neural networks. So feed-forward neural networks are something that have been around for a while. I decided to look for a random paper from a random book from 52 years ago, and I found this book that actually was published in 1972, so that's actually 52 years ago, that talks about feed-forward neural networks with no hidden layers at the time, talking about pattern recognition, weights adjusted by stochastic gradient descent, reinforcement learning, theory based on probability distributions of inputs and all those things. And I don't know where this guy went, but it was, if you read Spanish, it's actually scanned on a PDF. And there was actually an article in the main newspaper in Argentina talking about, we had a research group in artificial intelligence in Argentina at the time doing these things. And we were talking about sentience, and we're really worried about, that was the most powerful technology ever when we get to AI, and how we were worried about that they would take over the world, and it took 52 years, but maybe we're getting close to that point. But anyway, so what is the training problem for single hidden, let's say one hidden layer neural networks for simplicity? And let's actually start with the simplest problem, the only one thing I'm going to talk about. Let's assume we have linear neural networks. What I mean by that is the activation function is linear. I know that's a stupid problem, okay? I mean, why would you use a product of two matrices when you could just use one matrix? But the reason for studying that, I'll mention in a minute, is that it allows us to understand a little bit better. It's an idealization. It allows you to understand a little bit better some of the convergence issues, as well as this disturbed gradient descent problems. So So the question is simply that of minimizing the Frobenius norm, say, of a matrix Y times W2, W1 times X, where X, Y are the input-output pairs. I'll take X to be the identity for simplicity. So we just want to factor a matrix Y let me just go to the, I'll get to that. Well, yeah, so in the matrix factorization problem, I want to factor a matrix Y as a product of P times Q. Again, it's a stupid problem, right? I mean, I can factor it as X times identity, right? But it's actually an interesting problem, because if you think of neural networks, this middle dimension will be the hidden layer, okay? And one interesting question is not dimensionality reduction as with the first part of the lecture with encoders, but the opposite. What happens if you have a huge hidden layer, right? So the idea is to try to understand the idea of overparametrization. As I said, one of the reasons people want to look at this is to understand why overparametrization seems to work, which is a beautiful topic in itself. And I think we say a little bit about this in our paper, and I'll be happy to discuss with you later. This is, of course, from the standard paper of Belkin and so forth. That is the PNAS paper, right? It's not mine, but we know that the standard things that we know from statistics are not true, okay? And the question is why? All right, so this approach actually allows you to understand a little bit better why you actually get better convergence when you have overparametrization. So I hope to get to that. Anyway, but very quickly, what do we know about the gradient flow that you get when you have this? You just look at the Frobenius norm of Y minus PQ transpose. I'm putting the transpose just because I want them to be the same size. You look at the gradient flow, you can write it out. And we ask, the target set is the case where L is equal to 0, where we have exact interpolation of the input-output data, to use your terminology. And in fact, one can show that there's pre-compactness of trajectories in this case. Of course, everything is analytic. It's just polynomial of degree 2 or degree 3, actually. Polynomial of degree 3, when we look at the gradient flow, the critical points that are not in the target set happen to be strict saddles. One can actually prove that. And there's a number of references in the literature of people that have looked at basically that question. This is not per se new. What's new is sort of putting it all together in a package, but also understanding the effect of input. So you would like to have an ISS-Lyapunov function. If you try to write an ISS-Lyapunov function, the key point that happens is that, oops, sorry, I keep having the problem with that everybody has with this. You don't get an ISS-Lyapunov function because it's at some point the minimum singular value of Q and P becomes 0, then you have something, or even if they become very small, you don't have an exponential decrease in any way, right? You don't have a positive definite comparison function in this case, okay? So this is just a little calculation one can do. So let's understand a little bit better the dynamics, and the dynamics of the system are so beautiful. Let me even take the case where the inputs and the outputs are dimension 1, okay, and the middle has dimension 1. So the problem is I have a number A, and I want to factor it as B times C. I can factor it as, A times 1, 1 times A, A over 2 times 2, whatever, right? So anyway, that problem, when you look at the gradient flow for that problem, the gradient flow actually, when you write it out, it turns out there's a scalar factor in front, and then the rest is a linear saddle, a standard linear saddle. So all you have is a reparametrization of this linear saddle, but at some point the arrows reverse direction and you create new sets. So you end up having these two equilibrium sets, which are where the global minima are in green. This is what the flows look like, okay? All right? So the question is, what kind of convergence do we have? And we know that except for the stable manifold of the saddle, set of measure 0, you actually converge to the target set. One thing, I'm running out of time, so the one thing that I cannot explain, unfortunately, is that you can understand the advantages of overparametrization in this case, because one thing you can prove is that if you start with initial conditions around here, you converge much faster than you would converge if you just say do least squares, y minus x, y is given, you want to find x, so y minus x squared is minimum, okay? So if you just do that standard least squares, which will be no overparametrization, you actually will converge slower in general than if you do the overparametrized case. So it lets you understand a little bit this idea of overparametrization. Unfortunately, I will have to skip this. It actually tells you these ISS conditions, how they work. So let me skip all that because there's no time. But let me just say that you can put it all together, and this is just submitted. This is just submitted to the CDC for next year. But you can put it together, and you also assume you have the linear quadratic control problem, and you write the matrix as a product of matrices. So think a neural network to stabilize a system, okay? Like the kind of thing that you're looking at. Suppose you have a neural network to stabilize the system, and you train it using gradient descent. What happens? And to make the story short, because I don't have time to go through everything. Let me just go this one. You can actually show that if you actually look at that problem, so you have a feedback control problem, stabilization problem, look at it for take the LQ problem in infinite horizon, that gives you a stabilizing matrix, solving using a gradient flow, but write the matrix K as a product of two matrices, okay? And now do a gradient descent simultaneously on K1 and K2 in terms of optimizing. You actually can find that typically, not always, but depends on how K1 and K2 are initialized, you may have rates of convergence to your optimum, which is around here, the optimal value of the cost in that case, for the particular example that we're looking at, much faster than you would have with just doing the standard Kleiman, the Kleiman worked on this too, Athens and so forth work. So that's very new, but it's how you put together these ideas of neural network imbalance, and why you learn faster when you have basically how overparameterization can help you. Is that interesting or not? I have absolutely no clue if it's interesting in practice, but it's sort of an interesting intuition that something interesting is happening. So anyway, so that was 5 lectures. A lot of very smart people that did a lot of the work, and the pictures are there. And we can have questions. They'll kick us out of here, I think, so we'll have to have questions outside probably, but anyway. You can scan this for the